Hello, everybody. Let us resume our discussion on radiative transfer. Today, we will talk about a two level system which we started discussing last time. Let me first remind you of a few things which we'll have to use today also. So, these definitions. So, first, I have specific intensity. We have looked at it many times and we have written down the radiative transfer equation around it. So, this is the energy, say, absorbed, like dO for the time being, per unit time, per unit frequency range, per unit area of the detector or an area, per unit solid angle. You also defined spontaneous emission coefficient. Which we called, so this we called I nu. So this we called J nu. This is about the emission of energy. So the energy emitted per unit time, per unit frequency, per unit solid angle, per unit volume. We defined energy density of radiation, and what we will need is a connection of the energy density of radiation with the specific intensity. That is what we will need today, and this is in the case where the radiation is isotropic. So let me remind you that this is called isotropic radiation, and all these are actually specific quantities. So that's why I have a suffix nu in the right hand side of all of these. We had absorption coefficient. The way it was defined is, so I will write down the defining relation. Delta I nu absorbed was given by minus alpha nu I nu time ds. So ds is the length of the column or of the medium through which the light has traveled. It has traveled at this distance ds. The initial intensity was I nu, and this much of that is absorbed. Then alpha nu is the absorption coefficient. So here this is the quantity that is we are trying to define by this relation. We had the source function which we saw last time. What it is was just for the completeness, let me keep it here. So this was defined by J nu by alpha nu, essentially S nu is how we write it. And then let me write down the radiative transfer equation. In the both the forms. So one is with respect to S, so that is di nu ds is J nu minus alpha nu I nu. And then I can also write with respect to the optical depth tau nu, which we defined last time and saw what it actually means. Then S nu comes into picture. So these are the things that we have discussed. So let me just still be little more specific. In case of emission, the radiative transfer equation or the extra intensity that is added is J nu times ds. So that is something that we will use today. So I would like to keep it here separately. This is an extra information that is already there in the radiative transfer equation, of course, just like the definition of alpha nu is already there in the radiative transfer equation, but these are the things specifically we'll use today. So that's why I just kept in these boxes. So these are something that we have done so far: specific intensity, spontaneous emission coefficient, energy density, absorption coefficient, source function, and finally radiative transfer equation. What one thing that we have not spoken about yet is, for a given system, what will be our alpha nu and J nu? That is what we will talk about mostly today. But even if before we go there, let us discuss something about the shape of a spectral line. So now on, we will discuss in this lecture and the next lecture, we'll discuss two-level systems, which we started last time. So this is something that is giving rise to radiation, emission or absorption in the medium that we are talking about. Okay, and we kind of, if you remember, that it basically means that I have an upper energy level and a lower energy level, and there can be either an electron goes from the lower level to the upper level or comes back from the upper level to the lower level. The difference between these two energy level is h nu. So if I ever expect radiation happening in this frequency, then I will, if I want to plot the intensity as a function of frequency, and this is not thermal, then I expect to see a line at this frequency. What do I mean by line? I mean that if I want to really plot the behavior of this system as a function of frequency, so x-axis I am plotting frequency, y-axis I am plotting, say, the intensity, and there is only emission happening. It's not nowhere near to thermal equilibrium. So what I am expected to see here is that frequency is zero everywhere. Suddenly at the frequency of this, so let me call this nu naught, which is not telling you it's a particular frequency. Suddenly at that frequency, I will see that there will be some extra intensity and all other frequency it is zero. That is what I expect the intensity to behave, how the intensity to behave as a function of frequency. So this is expected if all radiation happens at a single frequency, nu naught. But it turns out that the reality is different. Whenever I will see, so these are called spectral lines. So this is the emission spectral line. Whenever I will see a spectral line, instead of this, what I will see is a spread around that frequency. Most of the emission will be coming at that frequency, nu equals to nu naught, but there will be emission at nearby frequencies also. So this is called the shape of the line, and the function that gives you this shape is called the line shape function. And why there is a shape of the line? It's not in a single frequency. And what are the line shape functions that one expect and sees is what we'll first discuss. Okay, so we are discussing shape of the line. This is given by a function, we call it line shape function. And it's usually denoted by phi nu. Okay. So what does it tell you? It tells you what fraction of the radiation is between frequencies nu and nu plus d nu. So this is what the line shape function gives you. Now the first question is that why should there be a spread in the line spread in the frequencies? So what brings in the spread in the frequency, and the spread in the frequency give you a finite width of the line, which we call line width. So question is what gives us spread. Spread is sometimes also called broadening of the spectral line. And gives it a width. So we'll talk about two ways you can get it, two completely different ways. The first one is because of uncertainty principle. So every energy level that you think of is not actually exactly one energy level which has an energy U or EL. Every energy level actually has a spread around it. And because of that spread, the transition frequency will also have a spread around that. So this is just coming because of the uncertainty principle, and it's a natural phenomenon. It happens. So this happens for each single atom. It's a natural phenomenon. Natural means that it is in the nature of the atom itself. It's in the nature of quantum mechanics. So this we call natural broadening. It can be calculated from the quantum mechanics of the level. Obviously, we will not be doing that. But once you calculate, it gets a line shape function which I denote with NL, and this line shape function looks like this. Let me first write and then explain what the different terms are. Okay. If you plot this function, it will look like the following. Obviously, at nu equals to nu naught, this term will be 0, and in denominator some term appears which is in square, which means that at that frequency it will be maximum. So nu naught, it will be maximum. It looks roughly like this. You can try to plot this in some suitable software and see how it looks. So it's called a Lorentzian profile. This function is called a Lorentzian profile. And you may have seen this function if you have done damped harmonic oscillator. This is the same profile that you get there. Okay. So it has the maxima at the frequency nu naught, and the spread is related to the quantity sigma NL. So sigma NL gives you the width or the broadening of the spectral line. You can ask the question, and this is I give you as a homework, what is the full width of half maxima? Short form is FWHM of the line. So what is the full width of half maxima? This is the full maxima. This is the maxima of the line. You calculate what is the value of phi NL there. Divided by 2, you get the half maxima. So what is the width of the line there is the full width of half maxima. Okay. That will be related to sigma NL, you will see. So this is what you get because of natural broadening. You see, this has a dimension of 1 by frequency. Width of the line should come in frequency because that's measuring the frequency axis. So you have one frequency in the in the numerator, and you have frequency square in the denominator. So phi NL has a dimension of 1 by frequency, right? So you can expect it to have a dimension of 1 by frequency, because remember what it was giving is, if I calculate this quantity phi NL, or any phi for that matter, so any phi nu d nu, this gives me the amount of energy coming in the frequency interval d nu around the frequency nu. So if I integrate over all nu, that should give me all the energy, right? So this is the fraction of energy coming in this frequency interval d nu around nu. So if I integrate over all nu, that should give me the entire fraction, and the entire fraction is supposed to be 1. So this is how it's called the normalization of phi. This is how phi is defined. Now if that is so, then phi nu must have a dimension of 1 by nu, otherwise it will not cancel out to be 1. So remember that phi nu has a dimension of 1 by nu. So if I ask you how much radiation is coming, so if I give you the total amount of radiation and ask you how much is coming at a given frequency, and you know the line width, you can all directly say that the total radiation times phi nu is the radiation around that frequency nu. Nice is the radiation per unit frequency around that frequency nu. Okay, so this is one type of broadening that we talked about, natural broadening, and it happens to each one of the atoms. There is another type of broadening that happens. It's because of random motion of many atoms. And this random motion is often thermal if the atoms that is emitting or observing has come into a thermal equilibrium. And for obvious reason, this is called thermal broadening. So here we called it natural broadening. So this is thermal broadening. Now this is not happening because one atom. So what thermal motion gives you, that say I have these gas particles. These are the two-level systems, which are the gas particles moving around, and they have random velocities in different directions. So when I look at them, each one of them, they will emit at exactly nu zero frequency, say, or absorb at the frequency nu zero. But when I observe, because of the Doppler shift, all these frequencies in my observation frame will be a little different, and it will be different for different of these two-level systems or atoms or whatever you want to say, molecules. That I have to account for while doing the observation. But you see, this is not happening for one single atom, but this is happening for a collection of two-level system. Collective motion rather. So it's not natural to them, each of them. It's the natural to the collection. That's why it's not called natural broadening. It's called thermal broadening. And the type of line shape function you get because of thermal broadening is given, is written here. I write this with T. And now this is a Gaussian, which is a familiar function to you. The spread of the Gaussian is written by sigma suffix T. T is the temperature at which the system is. Nu zero is again the center of the line. And sigma T depends on the temperature in the following way. It's all Doppler effect essentially. K is the Boltzmann constant, mass is the mass of each of these individual atoms. And if I plot again nu and now phi t, you know how a Gaussian looks like. It will be a more gently rising curve compared to a Lorentzian. The Lorentzian, in this part, it will be more spreaded. And the width is given by sigma t. So also calculate the FWHM here. So this is second homework. Okay, so that's about thermal broadening. Remember that it's basically happening because of the line of sight component of the velocities. Line of sight means if I'm looking from this side, this direction, if I call this z cap, then all these velocities of different atoms that I have drawn here, you have to take the z components. It's only that component which matters. because that is the only thing that will give rise to the Doppler effect that you are trying to look at. Okay, so two things to remember from here. So let me write those down. Number one, whatever be the reason, the line shape function has dimension of 1 by nu. Number two is that if a spectral line or let me write it this way, a spectral line emits finite fraction of radiation per unit frequency. That per unit frequency is coming from here because it is 1 by nu. The dimension is 1 by nu. Near phi nu. Near nu. So number two is essentially the definition of phi nu. We have talked about it earlier also, but just I wanted to keep this clear here. Okay, so with this much of introduction, which was quite long one, let us look at a two-level system in general. And what we want to figure out today is that for a two-level system, the spontaneous emission coefficient and the absorption coefficient, how are they related with the atomic uh, quantities, the quantities that you can calculate from the atomic physics, the quantum mechanics of the atom. So two-level system. Emission and absorption coefficient. So let me remind you what is a two-level system. So I have these two levels, energy upper level, energy lower level, difference h nu, number density here and up and down, three different types of processes that can happen. One is absorption, is this process that h nu photon falls into this. One atom goes from the lower level to the upper level. I can have spontaneous emission, that is radiation assisted emission. Where one atom comes from upper level to the lower level when a photon falls into it. Falls into the upper level, that brings an atom from the upper level to the lower level, and obviously there are two photons that will result. One was the original, the other is the new one. And then I can have a completely different type of case where it is not radiation assisted. We call that, sorry. So this is not spontaneous, this is stimulated because it is radiation assisted. So this is stimulated. Sorry. And this is not radiation assisted, so spontaneous. So that also bring a photon down from the top to the bottom. Sorry, an atom transits from the upper level to the lower level and a photon comes out of it. Okay, so both of these are emission, but one is radiation assisted and one is not assisted. That is how we distinguish them. Now, spontaneous emission, and now we'll write all the emissions with a positive signs because that adds photon to our net photons. So this we remember last time we wrote down AUL, so which is the Einstein coefficient, which we said could be calculated the uh, from the atomic transition physics, quantum mechanics of atomic transition. And it also depends on how many atoms are in the upper level. These two, so this is an emission, so it's in positive sign. So whenever there is an emission, transition from the upper level to the lower level, I will write that with a positive sign. So here, this is an absorption, so this comes with a negative sign, and this is given by, so it's assisted by radiation, and then it goes from lower level to the upper level, so B coefficient, VLU, and obviously N lower level, and this is an emission, so this is assisted by radiation, B upper level to lower level, and N upper level. Okay, and let me also remind you of how this A and B coefficients are related, because that we have to use shortly, that we arrived at last time from the case from considering equilibrium. So BUL is given by C cube by 8 by H nu cube. It's related to AUL this way, and BLU by BUL, this is GU by GL. You also remember that from the Maxwell's distribution, if these atoms are in thermal equilibrium, then Nu by Nl will be given by Gu by Gl e to the minus h nu by kt, h nu being the difference between the two energy levels. And obviously, the total number density of the atoms can be arrived at by adding up the number densities in the either levels. So these are the four important things that we looked at last time and will be of use today. Okay, so let us look at spontaneous emission and how the spontaneous emission coefficient I can arrive at from these spontaneous emission. So this is given by this term. So what this term is giving me is the number density of atom in the upper level, and this, remember, is this is a 1 by time dimension. So this term is essentially telling me, remember that the left hand side of this is how the upper level uh, number in the upper level changes, number density in the upper level changes. This is what is essentially all these things. So number of transition per unit volume, because these are number densities, and per unit time is given by AUL NU. So these many transitions are there. So this, remember that we are also assumed isotropy. So this transitions are emitting radiation isotropically everywhere. So if I ask the question, amount of energy emitted isotropically per unit volume, per unit time, and okay, so how much will this be? So this will be AUL NU. This is the number of photons. Each photon has an energy h nu. So this is the amount of energy emitted isotropically per unit volume per unit time. So now let me go to a little bit more abstract notation. So the amount of energy emitted isotropically, so amount of energy emitted, which I write with delta E, per unit time per unit volume. This is emitting isotropically, so I can easily find out how much is emitted in a given solid angle if I divide it by delta, divide it by 4 pi. So what all I have to do here is up to here is nu h nu by 4 pi. And I may want to also know how much in a given frequency range. And remember, to know that, all that I have to do is to multiply this by phi nu. So that gives me in a frequency range around that frequency. So if I ask the question, how much amount of energy is emitted emitted per unit time, per unit volume, per unit solid angle, per unit frequency range, this is the answer, right? Amount of energy emitted per unit time, per unit frequency range, per unit volume, per unit solid angle is nothing but the spontaneous emission coefficient. dt, d nu, d omega, and dv. So that is what I have here, dt, d nu, d omega, and dv. So this is nothing but the spontaneous emission coefficient. So now I know what is the spontaneous emission coefficient in terms of the atomic quantities. There is a little more to do, which we'll do shortly. So this h nu, so let me put a 0 over here, nu naught over here. This essentially is not any frequency, but the frequency at which the emission is happening. Okay, so everywhere there is a nu, I'll put a nu naught. Okay, so h nu naught by 4 pi AUL. For a given two-level system, these are constants. Even phi nu also I can say is a constant, but there is some modulus because phi nu has temperature of the gas, so that I have assumed to be constant for the time being. But the gas can be also in what we call the local thermal equilibrium, which means that it may change a little bit at point to point. And then I have this Nu. So let us see what is Nu in terms of the total number density. So Nu is the number density in the upper level only. And to find that, we need these two equations. So I have two variables, Nu and Nl, and I have two equations on Nu and Nl. So I can solve them and write them in terms of N, essentially, the total number density. If you do that, I am doing it say offline, and if you calculate Nu in terms of N, you will see it comes out to be this. This is very straightforward, so I am not attempted to do it here. You can even do it in your head. So once you use that, then the spontaneous emission coefficient can be written in terms of the number density itself. And let me, so this is also nu naught. One thing is very important to make note of is that what quantities in this expression are coming from the atomic physics directly. So you don't need to bother about the temperature or the number densities of the gas, which is a collective information, and what is coming from the gas. So here, like for example, the phi nu can have a temperature because the thermal broadening has a temperature associated with it. Here also I see a temperature sitting over here. This what I wrote as Nu is essentially N. So this N, this is N because Nu I have replaced. So these quantities, these three quantities here depends on the gas. Everything else is coming from the atomic physics. Okay. So if I ask the question, how much energy or how much intensity is added because of emission, specific intensity, how will I get that? What all I have to do is I have to integrate this J nu over ds, right? So this will stay outside. And for the time being, let us assume that the temperature is not a function of S. So that's one assumption that we are taking, remember. Then all this comes out of the integral. I get an integral over the number density over the direction of propagation. So this, what is this quantity? Well, say this is the light coming in from the left, the radiation coming in from the left, and this is the column of gas which is adding radiation to it, and I get excess radiation here, right? This integral is integrating over this entire S. So n, which was a number density, one of its dimension is integrated over. So what you call here, this is often written with a capital N. It's an integration over this column. So this has a name called column density. If you look at this expression, which we'll see in more detail in the next discussion, you see, if I assume again that temperature is independent of S, I knew the all properties of the gas that I knew depends on is the temperature, which we have assumed independent of S here, but it also depends on the column density of the gas. Okay. And that's a very important observation, because it's the column density and the temperature, then are the two things of the gas that you'll be able to figure out from this observation, from an observation of the emitted intensity. Okay, so one thing we have achieved is that we have been able to write down the emission coefficient Jnu in terms of the atomic quantities and the properties of the gas, which till now was just a black box for us. Let us look at the absorption coefficient in the rest of the time today. Again, if I come back to this picture, I can ask the question, what is the number of photon that is absorbed per unit time and per unit volume? That will be just addition of these two numbers. So number of photon absorbed per unit volume and time. So this is given by, so let's see which one will come first. This will be positive, the first term will be positive and the second term will be negative. So BLUNL minus BULNU, and the entire thing is multiplied by the energy density of radiation. I can write the same thing also in terms of specific intensity, because I know for a given isotropic absorption, in this case, with a photon number density u nu, there will be this much of, there will be I nu of isotropic radiation absorbed. So this is something, u nu is 4 pi I nu by C, that we saw also last time or last to last time, and we listed it somewhere here. We listed it here. u nu is 4 pi I nu by c. That's what I have used. So this is number of photon absorbed. So we can ask the question now. Energy absorbed per unit volume per unit time, so that we will agree to translate it to photons as photons to energy. I have to multiply by h nu. So I multiply by h nu, I nu by c. Okay, so let me write I nu separately. We'll see why. So h nu by c, I have a 4 pi, and forgot the minus sign. All right. I can do the same drill. So per unit frequency. So I get an extra factor of phi nu. So I get an extra factor of phi nu. And this is radiating isotropically. So I can do per unit solid angle. I have to divide by 4 pi. That cancels at 4 pi. Okay. Now all this is happening as the radiation is passing through this cylinder. The absorption is taking place, right? So there's more radiation here, less radiation here because of absorption. Also remember that when I say absorption, I include stimulated emission in it. So this is all that's happening with the radiation, and it is assisted by the radiation. So this, as I say, this travels a distance delta s, and this has the cross section delta a. So the volume I can write. So in the left hand side, I have a volume. I can write that volume as delta A times delta S, and then delta T, delta nu, delta omega. So this is the excess radiation. That is absorbed. The left hand side, if you look at carefully, I have delta A, delta T, delta nu, delta omega. So this is essentially the radiation absorbed by delta S, which I bring into the right hand side. So I get I nu, then this H nu by C phi nu, PLU NL minus BUL NU, and delta S. Okay. So this is the radiation absorbed. So if I ask how much radiation is added, so I put a minus sign over here. So this minus sign say radiation added. Now if you look at, so delta I nu equals minus I nu something times delta S. And if I go to the top for the absorption coefficient, delta I nu equals minus something times I nu delta S. So that something is essentially my absorption coefficient. So let us come back here. So this is essentially my absorption coefficient alpha nu. Now what I can do is I can take these things common outside. So let me write alpha nu. If I take those outside, I get this. Now I will skip a few steps, but something is already done. This NU, we have already written in terms of the number density, and here I have BLU by BUL, NL by NU, BLU by BUL. I can write in terms of GU by GL, and then I can use this. So I will not be doing the steps, but imagine that I have used these expressions, and finally should be able to write down alpha nu in this compact form. It's again very straightforward manipulations, so I skip it doing it here online. And we'll use this expression in next class, next lecture, where we will talk about a particular two-level system which is of enormous use in astronomy as well as cosmology. So you see now again, just like for the emission coefficient, the absorption coefficient also we have written down in terms of the atomic quantities and temperature and number density. So that's it for today. I'll stop here. So let me remind you what we have done today. We have discussed about the line shape functions, which gives you the fraction of radiation happens in a given particular frequency region for a given two-level system. Then we figured out what are the emission and the absorption coefficient in terms of the atomic quantities which comes from the quantum mechanics of the atomic transition and the properties of the gas for both emission and absorption coefficients.